Time crystals, with many of their unique properties yet to be understood, represent a significant breakthrough in the field of physics. First proposed in 2012 and experimentally observed in 2017, time crystals continuously evolve with structures that periodically repeat in time, akin to how ordinary crystals have spatially repeating structures. A traditional crystal breaks translational symmetry in space by positioning its atoms at regular intervals, leaving other locations empty. Similarly, time crystals break translational symmetry in time, with their structures periodically changing over time. Researchers have built systems of interacting particles that, intriguingly, appear to oscillate autonomously, driven by periodic forces. This phenomenon differs from the theoretical time crystals proposed by Nobel laureate Frank Wilczek in 2012, which were suggested to break continuous time symmetry and oscillate indefinitely without external energy input. Instead, the newly observed systems exhibit a type of broken discrete time symmetry. Wilczek's original proposal defined time crystals through the highly ordered lattice structures of physical crystals like salt or diamond. In physical space, crystals break translational symmetry because atoms or molecules occupy distinct, regularly spaced positions. Similarly, Wilczek theorized that even in their lowest energy state, a system of particles could spontaneously form a periodic structure in time, thus breaking temporal symmetry. He suggested that a static magnetic field applied to a ring of quantum particles could encourage them to cluster and rotate continuously, akin to a perpetually moving machine. However, this idea faced significant criticism, particularly from Patrick Bruno at the European Synchrotron Radiation Facility, who argued that such a system could not be in its ground state while rotating, thereby questioning the physical feasibility of Wilczek's time crystal. Despite these setbacks, Wilczek and his colleagues adapted their approach to focus on systems not in true thermodynamic equilibrium. These discrete time crystals are driven by periodic forces applied to an array of spins, causing their orientations to oscillate at integer multiples of the driving period. This breaks the discrete time symmetry imposed by the driving fields, analogous to how introducing distinct atoms at regular intervals breaks the surface symmetry of a crystal. Christopher Monroe, leader of one of the experimental groups from the University of Maryland, highlighted two critical features of these time crystals: rigidity and the absence of heating. Rigidity refers to the system's ability to maintain a constant oscillation period despite changes in external parameters. Although the system requires energy to oscillate, it must avoid heating to remain in a quasi-equilibrium state. Monroe's team created time crystals using trapped ions. By subjecting about a dozen ytterbium ion spins to periodic laser pulses, they operated the system at a specific rate. Additional laser beams introduced randomness to each spin's rotation, preventing the system from heating. Remarkably, the oscillation period of the spins remained constant even when the pulse period varied slightly, indicating a property similar to the fixed lattice structure of a conventional crystal. Continuing from the previous discussion, another experiment led by Mikhail Lukin from Harvard University used a more natural but less precise setup. This experiment involved approximately 1 million spins created by nitrogen vacancy, NV centers, which are impurities in diamonds. In this system, the driving field was provided by microwave pulses, while the natural noise resulting from random variations in dipole interactions between NV centers helped suppress heating. In this arrangement, researchers successfully observed spins oscillating at integer multiples of the driving period, particularly at twice and thrice the length of the period, and remaining stable despite changes in driving parameters. However, it was noted that future experiments would provide more compelling evidence if they could demonstrate that the spin oscillations remained in phase for exponentially longer times compared to certain system parameters, such as the physical length of the oscillations. Frank Wilczek acknowledges that these findings do not constitute a fundamental breakthrough akin to rewriting the standard model of physics, but he emphasizes that the ability to spontaneously break discrete time symmetry is a qualitatively new phenomenon. Wilczek also suggests possible practical applications of this research, including the development of clocks for quantum computers. He points out that these time crystals oscillate reliably and exhibit long-range correlations that could be highly beneficial in advancing quantum technology. In conclusion, the experiments conducted by Mikhail Lukin and Christopher Monroe represent significant steps toward realizing discrete time crystals and validating theoretical predictions with experimental evidence. While these findings have sparked some debate regarding their broader implications and innovations, they undoubtedly open new avenues for exploring non-equilibrium phases of matter. In Japan, researchers have developed a new mathematical technique to study the properties of time crystals. A team led by Kei Nemoto at the National Institute of Informatics in Tokyo used a combination of graph theory and statistical mechanics to explain how these exotic quantum materials evolve. This groundbreaking work paves the way for practical applications of time crystals, such as simulations of complex quantum networks. Initially, there was significant debate about the existence of time crystals in nature. However, recent theoretical and experimental studies have demonstrated that certain non-equilibrium quantum systems can indeed form discrete time crystals, DTCs, when driven by a periodic external force. Nemoto's team further investigated discrete time crystals, DTCs, using graph theory, which models complex discrete systems as interconnected groups of nodes. In this context, nodes represent various states of a DTC. By mapping the asymmetric connections between states, the researchers were able to accurately predict how the system would evolve under different conditions. One significant finding was that a DTC could melt when excessively strained, ceasing to oscillate and losing its time crystal order. To delve deeper into this phenomenon, Nemoto and colleagues combined graph theory with statistical mechanics to model the evolution of a DTC's graph structure until it completely melted. Although the practical applications of these materials are speculative, the results revealed how DTC properties could be used to simulate complex interconnected systems. Using innovative tool sets to translate DTCs into the language of graph theory, Nemoto's team demonstrated that these materials could simulate networks as extensive as the global internet using only a few qubits. Additionally, they showed that DTCs could be used to achieve quantum simulations of quantum many-body systems, which are notoriously difficult to model. With further development, the researchers' techniques could be suitable for applications in advanced machine learning algorithms, the analysis of natural ecosystems, and simulations of neural structures in the brain. This research marks a significant advancement in understanding and potentially harnessing the unique properties of time crystals. Thank you for listening. Take care.